That was loud. And here we go. So guys, there you have it. This is what we're doing today. We're starting chapter 6 by talking about electromagnetics and waves. Today is the 14th. Yeah. What just happened? Oh, it's frozen. Sorry. There we go. So guys, today we're talking about electromagnetics and waves. And today's the 14th if you want to date your notes to keep things in order. But guys, Brandon asked a second ago, do we need our books? And I said no, which isn't to say we're not going to reference the books. I was just hoping that after having done the chapter outline, it was familiar enough to you that you didn't need to actually have it in front of you to think through what it was about. So guys, mentally, and maybe you can think through what you did for your chapter outlines that you turned in. Guys, what was chapter 6 all about? Electrons. The entire stinking chapter was about electrons, right? And did you have that experience as you were doing your outlines when you were like, oh crap, oh crap, oh crap. I know this stuff. Did you have that experience? What was the oh crap stuff? Spectra and waves, right? And then when did it start to feel like a big old familiar hug? And the SPDF, energy level, sublevel, orbital spin stuff, right? So guys, that was the experience that, is it okay? That was the experience that maybe you should have had. All of this stuff that was unfamiliar, that all of a sudden became really familiar and comfortable. So guys, let's talk about this. What's the connection? Why would a chapter that ends with this stuff, right? All the energy level, sublevel, orbital spin. Why would a chapter that ends with electron structures start with waves? What's the connection? Because we didn't really make the connection last year. Go ahead. Okay, so we understand that it has to do with electrons moving. Yeah. Right. Right. And so the falling electrons from excited to ground state release light. And guys, do you all understand light is a wave? And then if we put those ideas together, we understand that if we can study the waves of light that are released when electrons fall, we can do this backwards as we discussed in lab a couple minutes ago. And if you weren't in lab, that's fine. But guys, we can work this backwards and we can figure out where the electrons are going from and to. You get the idea? Now guys, in order for this to make sense to you, there's one important thing that you've got to make sense of. Guys, is light a thing or is it a wave? Which one is it? Is it a particle or is it, and a lot of you know the answer, is it a particle or is it a wave? And the answer is yes. Electrons are fully particles and electrons are fully waves. Now guys, here's the problem. Some of you are now trying to put that together mentally, and what you're picturing then is you're picturing that an electron is a particle and that particle moves like a wave. Yes or no? No. Guys, electrons are particles that do not move as waves, and there are waves that are not made of particles. So guys, and I know that this is crazy. It's called the wave-particle duality of nature. And if you want to look it up, you can. We're not going to get into the deep recesses of it. But guys, here's the thing, because we're going to treat light as both a particle and a wave. And you've got to understand that when we say that light is a wave and light is a particle, these are not particles moving as waves. They're actually both independently of each other. Again, it's called the wave-particle duality of nature. Now, guys, here's a term you need to know, and we're going to get to it in a minute. But, guys, what do we call light when it behaves as a particle? We give this particle a name, and do you know what it is? They're called photons. And so, guys, when we treat light as a particle, we call these photons. photons of light. You can think of them as being bullets. In the same way that a bullet transfers energy, and that's what makes them deadly, because they transfer a lot of energy. Guys, we are going to treat light as a particle. They are called photons. But we're also going to understand light as a wave, and the two do not conflict with each other. You can perfectly describe light as a wave. You can perfectly describe light as a particle. So what determines which one it is? It's depending on what we're measuring. Guys, it turns out that if we study light as a particle, it behaves as a particle. And if we study light as a wave, it fully functions as a wave, which I know makes no sense because it almost seems as if light knows that it's being studied. And that's obviously not true. But guys, there's something fundamental about our universe that says that very small things can be both particles and waves simultaneously, and they don't pick which one they are until we study them, and then they pick the one that is in keeping with the way that we're treating them. Crazy, right? But it gets worse. What about electrons? Are electrons waves or electrons particles? They are also both. So guys, we talk about this because what we're going to do is we're going to treat we're going to treat light as waves. And again, where does light come from? Falling electrons. And so now we've got this interesting idea because we always treat electrons as particles, and these particles, when they fall, release waves. And you're going to find out that that's not so big of a stretch because at the same time that light can be particles, so can electrons. And then what we're going to do today, we're going to treat it that way. We're going to say electrons are particles and they release waves. At the end of today, we're going to say, what if we treated light as a particle? We're going to call them photons, and we're going to talk about energy, and we're going to relate that together. Then, guys, there's going to be an intermediate day, and then guess what we're going to do? We're going to start treating electrons as waves, and that's where these pictures come from. So guys, all of this, and here, let me remind you. Guys, we way skipped over this last year. Remember this diagram from last year? Where we talked about atomic history, and we talked about the idea that Rutherford discovered the nucleus. He thought the electrons were still mucked together in the plum pudding model, and then Bohr came along and he studied light, and he figured out that the electrons were actually organized, but he was trying to treat these electrons as particles, as if they were planets revolving around the nucleus. We call it the planetary model, and then we attribute the break from that to Schrodinger, where he figured out that electrons actually behave more accurate. Well, our models are more accurate when we treat them as waves rather than particles. And guys, we didn't talk a lot about this gray area, but understand that this gray area is actually there because light and electrons can both be expressed as particles and waves. And when those two ideas come together, combined with the idea that electrons release light, that's where this gets really interesting. Do you get the idea? Yeah.
So what you're saying is...
Never try to tell me what I'm saying because I don't know what I'm saying. Go ahead. No, that's interesting, Jake. Jake said the Bohr and Schrodinger models are equally correct. And no, because... And it gets even worse because it turns out that Bohr actually did some of this as well. That Bohr, as Bohr was working on this model of the planetary model, and we'll watch a video later. It's fascinating stuff. As Bohr was developing this planetary model, he was starting to see problems with it, and he suspected that there was something else going on. It was Schrodinger that fleshed that out by saying, let's apply the equations that we already know describe waves. Oh, I got too close. Let's use those equations to describe these as waves rather than particles. But Bohr was starting to move in this direction. People like Einstein hated it. Einstein actually almost threw punches with Schrodinger because he's going, this is stupid, it can't be. So there were people in here that hated this transition, but Bohr suspected it was right. With that said, Bohr knew that this model was incomplete. And the reason is because while, yes, it is okay to treat electrons like particles, these particles are not moving around the nucleus like planets. In fact, these particles are in all possible positions simultaneously until you locate them. So this planetary model is pretty darn completely wrong. And the wave model's better. But it doesn't mean particle is wrong.
In terms of like representing the way photons are emitted.
Yes, right, exactly. Oh gosh, and that's where we're going to start today, that when we think about how photons are emitted, we're going to talk about the idea that these electrons are falling from higher orbits, if you will, to lower orbits, just with the idea in the background that these orbits are not spherical, they're actually diffuse cloud-like structures, but the particles are still moving between them. Yeah. Guys, anything else relative to this? Because I know that we're drawing on stuff that you either understood or believed you understood, and that's why I brought this up, because I wanted to bring you back to familiar ground before we, forgive me, but jumped forward and into this idea of waves and the connections. So anything else you want to explore there, or can we get into waves? You're okay? Okay, so guys, in order for us to make this leap, if you will, we need to go back a little bit, because it's not okay for me to assume, well, maybe it is. I don't want to say this in the negative. Have you all taken physics? All of you have? Okay, well, I know. How do I ask? Because if I say, who hasn't taken physics? You go, I haven't. And then you feel stupid. So guys, if you've taken physics, you should know this. If you haven't, here's what you need to know. So guys, when we talk about electrons, we need to talk about waves, not just because electrons can be described as waves, as we'll find out later, but because these electrons release waves, which we call light. And so guys, when we do this, and this is stuff you probably want to get in your notes if it's not familiar, the reason that we're talking about waves is because the source of a lot of what we know about electrons is actually revealed to us through the emission of light as these electrons go from excited to ground states, and even vice versa, although we don't talk about it a lot. And so guys, the idea here is that light is sort of our initial window into electrons. So when we talk about light, we need to first of all appreciate that light is just one type of what we call electromagnetic radiation. Now guys, radiate, of course, means to transfer energy, but this energy is transferred through what we call electromagnetics. And if you've taken physics, you know that there's a tight correlation between electricity and magnetism. You take a wire and pass electricity through it, and it creates a magnetic field. Similarly, if you take a wire and pass it through a magnetic field, it creates electricity. Guys, electricity and magnetism are very tightly linked in the world, the universe in which we live. Well, it turns out that this link between electricity and magnetism also applies to the subatomic world of radiation. So light is one type of what we call electromagnetic radiation. Because electromagnetic radiation then is a form of energy that has a wave characteristic, and it travels through a vacuum, which is fascinating. It doesn't require a medium through which it transfers. Which is pretty cool. Now guys, the first thing that we need to understand about this electromagnetic radiation is how fast does it go? The speed of electromagnetic radiation, which we actually call the speed of light. So guys, all forms of electromagnetic radiation travel at the speed of light. So if you take a second and grab your AP equation sheet, you will notice that that value is given to you on the sheet. So obviously we are on a new section of this. We're done with the thermochemistry section. So now we are on the atomic structure section of this. It's on the page 3 side. And you'll notice there, guys, we've only got 2 equations under atomic structure. And both of these equations we're going to learn today. But then you'll notice that the speed of light is given there. And they give it as 2.998 times 10 to the 8th meters per second. Now, guys, understand that that's the value that you will use on the AP equation sheet. But our book actually gives you a different value. Our book uses 3.0, I think, did you guys? 3.00 times 10 to the 8th. You can use either one, but we will stick with what the equation sheet says, which is 2.998. Yeah.
So if a meter is if the distance light can travel in a second. Oh, no.
Well, it's not. I mean, 300 million meters is the distance light can travel in a second.
Well,
Yeah.
I remember what exactly a meter is derived from, just how far light can travel.
Oh, you're working this backwards. So it used to be that we defined the meter as 1/10 millionth the distance from the North Pole to the equator. That was the original definition. But because of tectonic shifting, that distance is always moving. So what we've done is we've redefined the meter based upon a wavelength of light. And frankly, you can look it up. I don't remember what it is, but it's now based upon like the wavelength of light. If the energy is so many, I don't remember, but you're right, they do it, yeah.
So if that's the case, then how come this number
Isn't very nice?
Yeah, I mean like 2.0, why is it a rough number?
Well, just because we create a standard doesn't mean that the things that relate to that standard will necessarily be round. It's not like the atomic mass unit that we said equal to the mass of a proton, and now protons weigh 1. This is actually a number that was based upon another measurement that we just sort of associated with light eventually. But it wasn't originally, the length of a meter was not initially set based upon the speed of light. It was set upon a distance, and then later we related it to a wavelength. Not a speed, and maybe that's the missing piece, is that the definition now for a meter is not based upon a velocity of light, it's based upon a wavelength of light, which then over time gives us velocity. So,
Because the meter didn't change.
correct, yes, and because the meter didn't change. Yeah, go ahead. I don't think they'll like that. I would, yeah, not when in doubt, but when referencing, use the values on the table, on the chart, on the equation sheet. Okay, so guys, let me then share this with you. And I suspect some of you understand and appreciate this, but let me draw you into this idea of light is a type of electromagnetic radiation. I really like this diagram. I lifted it off the internet. But guys, it's interesting, and some of this should be familiar to you, that if we describe light as a wave, guys, waves have what we call wavelengths, and we'll define this more in a minute, but a wavelength is literally the distance between 2 repeated points on a wave. It could be, can I do this? Crest to crest. It could be point of inflection to point of inflection. It could be trough to trough. It doesn't matter. If we look at a wave, the distance between 2 repeated points is the wavelength. And guys, this is the electromagnetic spectrum. And remember the colors, right? We've got Roy G. Biv. Is Roy red, high or low energy? Low, and then Biv, violet, are high energy. So guys, this spectrum is in order from low energy all the way over here to high energy. So what is the difference between these different types of electromagnetic radiation? And the answer is wavelength. So guys, at the very low energy end of the electromagnetic spectrum, we have radio waves. And guys, the waves for radio waves are about 100 to 1,000 meters long. So picture a football field to about a half a mile. So when you tune into KOHS, your radio is actually picking up waves that are somewhere in length between the length of a football field and about the height of a building. Now, interestingly, and we're not going to do the math right now, you can actually calculate how long the waves are. What would you need to know about KOHS in order to do that? It's 99 point what? 91.7. But guys, that is 91.7 megahertz. So that means that there are 91.7 million waves that come out of that radio transmitter every second. So if you were standing somewhere in space and if you could see radio waves, you would see about 92 million waves go past you in a second, and those waves would be about 100 to 1,000 meters long. But you're going to find out that we can actually figure out how long the waves are simply by knowing how many waves pass a point in a second and the speed of light. And so guys, that's the only difference between all the different radio stations on the FM dial, is different radio stations are assigned different frequencies within the radio spectrum. And then if you ever listen to AM radio, that's actually in kilohertz rather than megahertz. That's why music is on the FM dial and talk radio is on the AM dial. Guys, AM radio is actually sending out data in thousands of cycles per second rather than millions of cycles per second. So FM radio can carry more data, and as a result, you end up with music on the FM scale and you only end up with talk radio on the AM scale, except for country music on the AM stations, and then it sounds horrible because they can't carry enough data. Interesting, right? So that's the difference between the two. Yeah.
So when the sun hits rain, creates a rainbow, are we getting, is there above the red, is there going to be this whole infrared microwave to radio?
Yeah, so let's get there in a second. It's an interesting question, and there's an answer, but let's get there. Okay, so then guys, what happens when these waves become smaller? Well, when we end up with waves on the order of about a centimeter down to a millimeter, now we're in the microwave band. So guys, the waves that come out of the magnetron in your microwave that heat your food, actually those waves are about between a centimeter and a millimeter. How do they make your food warm? Any of you know? They actually make the water molecules inside your food wiggle, and when they wiggle, they rub up against each other, and the friction actually causes your food to get warm.
So is that where there's like that fine mesh?
Yeah, it turns out that fine mesh in front, yeah, because you look in through the thing and there's the screen with all the holes in it. The size of the pores, if you will, in that mesh are actually just the right diameter so that it's enough to interfere with those waves, because the size of the holes are similar to the wavelengths of the energy, and it can actually filter it out. Yeah, interesting, right? But the visible light from the light bulb inside your microwave is smaller waves that can get through the hole so you can see. Yeah, not bad. You guys want to do an interesting experiment at home? This actually really works. Go home and buy a big old, well, not home, go to the store and buy a big old Hershey's chocolate bar. And then unwrap that Hershey's chocolate bar and put it in a microwave-safe glass pan. Put it in your microwave and then shut off the turntable. Because guys, understand that the microwaves that come down out of that magnetron are actually very regular. That thing that's shooting the microwaves is always repeating itself. And so as these waves come down, as they hit the food, if the food didn't move, those waves would always be hitting the food at the same point in their wave-like pattern, and you wouldn't end up getting effective cooking. You get hot spots. That's why you've got that thing. Well, that spins. Well, if you turn that thing off, and then if you put a candy bar, a chocolate bar in your microwave and then cook it for a couple minutes, if you do it just right, and if you stop at just the right moment where the chocolate is just about to melt, you can actually see the wavelength of the microwaves in the surface of the chocolate bar. Yeah, it's really cool. Yeah, Google it first if you want to. Well, maybe don't. You could, if you Google it, you'll see videos on YouTube. But try it. Go home and get it, and it's got to be not one of those. It's got to be flat. So you may want to flip the. You know how they put the scores in the chocolate bar? Flip it over so the smooth side is up, and then try it. It's actually really cool. It works. So then, guys, as we get down to smaller waves, now we're on the order of wavelengths like protozoa. We're into the infrared range. Now we get into visible light. And guys, the wavelengths that our eyeballs can see are interestingly have wavelengths about the size of bacteria. But then, guys, as we get smaller than that, ultraviolet waves have wavelengths on the order of the size of molecules. X-rays have wavelengths on the order of atoms. And then gamma rays have wavelengths on the order of atomic nuclei. So, Jake, you asked the interesting question. When we see a rainbow, first of all, how does it work? And what happens is this. If this is a raindrop, and if this is our sun, and then if this is us, what happens is the sunlight goes into the front of a raindrop, and it breaks into a spectrum. Then the back of the raindrop reflects it back, and we see it as a rainbow. And if you get millions of different raindrops, that's how it works. But you will only see rainbows if the rain is in front of you and the sun is behind you, because the raindrops actually work as a prism and a mirror. But the answer to your question, because you said when we see rainbows, do we also get infrared and ultraviolet? And the answer is yes, because sunlight contains infrared and ultraviolet. Although there is the possibility that the ultraviolet has enough energy that it just penetrates the raindrops without being scattered and reflected. Go ahead. Some of it does, not all of it. But what you're saying is correct, that the sun releases typically energy in all of these different wavelengths and energies, and some of it gets absorbed, some of it passes right through us, some of it gets scattered in our ozone layer. What happens to it depends on what it's passing through. But absolutely. Just a second. Go ahead, Tyler. Yeah. Right. Exactly. Yeah, so what happens is that the best example that I can think of is if you've ever seen these telescopes that they're building now, because the limit that we're having with telescopes now is the dishes on these telescopes are so big that they deform under their own weight. So what they're doing now to build telescopes is they're building them of billions of little mirrors that are then supported against a matrix. And that's kind of what goes on with these raindrops. If the storm is just right, you end up with a wall of water. And even though it's made up of billions of raindrops, those raindrops act collectively as a wall of water. They all behave as if they're just one big wall of water that gives you one mass reflection. But it's actually made up of billions of little reflections. Yeah, it's really cool. So guys, you comfortable with this idea? Go ahead.
So, I mean, is it only visible light that's emitted from electrons falling, or do we get ultraviolet?
No.
So microwaves.
Oh yeah, absolutely. Yeah, guys, but understand it's not the full gamut, because electrons in many instances are too big. They're too big to emit gamma, and they're too small to emit radio. But the thing that's crazy, and we're going to talk about this a little bit, it turns out that, I even fear to say this, anything that moves releases electromagnetic radiation. So when you walk out the door to go to lunch, you're releasing electromagnetic radiation. It's so low energy that it's way longer than radio. But in theory, anything that moves in our universe, anything that moves releases electromagnetic radiation. So including us. It's ridiculous. Yeah, actually. Very low energy photons, but yes, go ahead. What does it do to what? Oh, that's a whole different process. Yeah, it's a whole, it actually arcs, but that's an electronic thing. It's not a light thing. So you guys getting the idea behind all of this? Is this okay? Okay. So guys, what we need to do now then is we need to bring in an interesting other idea. So notice that this diagram is not the same. How is it different from the one that you just saw? It's flipped backwards. Now gamma is on the left and infrared is on the right. Don't take any, or I'm sorry, radio's on the right. Guys, don't take anything away from that. It's just, this is the diagram that's in your book. And what I wanted to do was now draw your attention to an interesting other, because what this has done is two things. Here's our wavelengths, right? And so we understand this idea of wavelength, and it is now in meters. So down at gamma, we're 10 to the negative 11th meters. And then we move up to about a kilometer, which we said is out here into the radio frequency. But now, guys, notice what they've done. Can I do two? Can't. So, guys, notice what they've done is they've now broken out this very narrow band that we call visible light. So, guys, let's talk about this. What is special about visible light? And the answer is nothing. Guys, the only reason that visible light is interesting to us is because our eyeballs were either created or they evolved to be sensitive to this particularly narrow band of the electromagnetic spectrum. Now, guys, why is it that our eyeballs are sensitive to this narrow band? And the answer is because this narrow band has a series of wavelengths that are able to make molecules in the back of our eyeballs twist. You guys know how seeing works? You've got rods and you've got cones. And guys, in those rods and cones are these really cool molecules, and they're quite long. And what happens is when light hits these molecules, it causes the molecules to twist. And there are atoms hanging off the sides of these molecules that create polar interactions with each other. And what happens is when these molecules twist, these atoms move relative to each other. Their polarities change. And those polarity changes create currents. And those currents travel down our optic nerve into our brain, and they get interpreted as color. So the greater the energy, the more the twist, the more violet the color. The lower the energy, the less the twist, and the redder the color. And so, guys, our eyeballs are finely tuned. Evolution, creation doesn't matter. They are finely tuned to be sensitive to these particular wavelengths of light. But guys, understand this thing we call the visible spectrum is just a series of wavelengths that sit between the ultraviolet and the infrared spectrum. All of this is just human experience. Yeah. Absolutely. There are animals that can see into the infrared, and there are animals that can see into the ultraviolet, or at least we think they can, because they can't tell us, but we shine ultraviolet light at them and they kind of freak out. Yeah. I don't know the limits to it, and I'll lay this on you, but guys, do you know that you can see infrared light? Please don't try this. I know you're going to try it. Just trust me on this. Guys, you actually and when I say don't try it, I mean don't do it now. In addition to stick a candy bar in the microwave, guys, maybe you don't understand that you all have infrared emitters. That's how remote controls work. This little diode at the end of this is actually an infrared light bulb. It's an LED. It's not really a light bulb. But just like the LED light that's the flash on your camera, guys, this is also an LED light. It just emits in the infrared. And so when you push this button, which I'm not going to do because it could change well, here I can push freeze. So when I push this, I didn't even see it. But when I push this button, what happens is it releases increases, something like Morse code. It goes flash, 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 flash. And it's really flashing long and short, just like Morse code. And what happens is each one of these buttons has its own Morse code that goes and that bounces or goes to the sensor, and the sensor picks that up and goes, oh, this means freeze the screen. But all these are infrared emitters. Well, it turns out that the camera on your cell phone can actually pick up that infrared light and translate it into visible light. So if you take the camera on your cell phone, point your remote control at it and push a button, you can actually see this light up. And you can actually see the flash, 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 flash. You can see the Morse code that is associated with each one of these buttons. Try it at home. Because many times cell phones are actually sensitive into the infrared, and you can see those colors. You can see the lights flash. So kind of interesting. All right, so guys, with that said, here's the leap that we now need to make. So we understand this idea of wavelength. We understand that it's in meters, and we understand that short wavelengths are high energy and long wavelengths are low energy. Well, now, guys, we've got to talk about this. We've got to talk about frequency. We not only describe waves based on their length, we also describe them based upon how many of them pass a fixed point at any given amount of time. Now, guys, if you don't understand frequency, think about it this way. Imagine that you're on the Pacific coast. I was there over the summer. And you're sitting up on a bluff above the coast, and you're just sitting there hanging out watching the waves come in. And then imagine that you start a stopwatch and you start counting waves. And you're like, ready, go. 1 wave, 2 waves, 3 waves, and a minute later, you count 12 waves. Well, guys, the frequency of the waves in the ocean at that moment would be 12 waves per minute. That's all frequency is the number of waves that cross a fixed point in a given amount of time. Now, guys, obviously, when we're talking about light, to try to count waves in minutes would be ridiculous. So instead, we count them in seconds. And so, guys, when we talk about the frequency of electromagnetic radiation, we do it in seconds. But it's waves per second or just inverse seconds. It's really 1 over seconds. And so when we talk about the frequency of waves, we do it in inverse seconds. Now, guys, with that said, check this out. So down here, we have very long waves. But guys, look at the frequency. The frequency of radio waves is somewhere between 10,000 to 1,000,000 to 100 million. And now you're going, dang it, 100,000 to 100 million waves a second, that's a pant load of waves. Not if you're light. Because guys, the other end of this is 10 to the 20th waves per second. So relative to how many waves come out in electromagnetic radiation, 100,000 is none, because we go up to 10 to the 20th waves. So now, guys, look at the relationship. Radio waves, are these long or short? Long waves have low frequencies. But then, guys, look down here. These are little itty-bitty short waves. What's true of their frequencies? They're freakishly high. If you've got waves as short as gamma rays, you're going to find out that you've got a pant load of those waves passing a fixed point in any given amount of time. So now you're probably suspecting this. There's a relationship between these two. And guys, there is. Because what are our units here? Meters. What are our units here? Inverse seconds. And if you have meters on top and if you've got seconds on the bottom, what do you have? Velocity. And what is the velocity of all electromagnetic radiation? The speed of light. Guys, it's not just light that moves at the speed of light. All of these move at the speed of light. And because the speed is a fixed point, when this goes longer, this goes shorter. And when this goes shorter, this goes faster. And that relationship always holds true. So guys, it plays out like this. You ready? So we understand that waves are described by two factors. First of all, wavelength. And guys, wavelength is abbreviated with this. This is the lowercase Greek letter lambda. Capital lambda actually looks like this. We go lowercase. And guys, lambda, or wavelength, is the distance between two repeated points, and it is measured in the units of length, in this case meters. Now guys, with that said, we run into a problem. The other descriptor that we use for waves is not amplitude. We are not concerned about the amplitude of electromagnetic waves. Doesn't mean the light is brighter. We'll talk about brightness in a minute. But guys, it doesn't mean the light is brighter. We don't care about amplitude. So what do we care about? Frequency. And guys, frequency is abbreviated with the lowercase Greek letter nu. That is not a V. That is the lowercase Greek letter nu. And frequency then is the number of waves that pass, well, crests, but waves. The number of waves that pass a fixed point in 1 second. And guys, the units for this are measured in hertz or inverse seconds. So those inverse seconds are actually called hertz. So now guys, when you go out and buy a computer and you just bought a 1.2, what are we measuring it now, gigahertz? I don't even know, I bought a computer in a while. But if you buy like if the processor in your computer is a 2.5 megahertz processor, that means that computer can do 2.5 million calculations in a second. We're in gigahertz now. So guys, these are the two factors that we care about when we talk about waves. We care about wavelength, lambda, measured in meters, and we care about frequency, nu, measured in inverse seconds or cycles per second, which we call hertz. Y'all caught up? You're good? Okay, so let's bring them together. Guys, the trick is this. When we bring frequency and wavelength together multiplicatively, the product of these is equal to speed. I showed that to you a second ago. You got meters, you got inverse seconds, multiply them together, you get meters per second, which is velocity or speed. Now guys, this is what this looks like. The speed of a wave is equal to lambda nu. But if we're talking about light, then speed is actually the speed of light, which is abbreviated c. That's the same c is equal to E equals mc squared. C is our abbreviation for the speed of light. So now, guys, we have an equation that we can use to figure out the relationship between wavelength and frequency for waves. It says the speed of light, assuming it's electromagnetic radiation, is equal to the wavelength lambda times the times the frequency nu. Now, guys, find that on your equation sheet. You got it there? You're okay? You're good? Yeah. Because the other C is the heat capacity. It's different. Okay. It's contextual. We'll say this. When you're figuring out the velocity of light, don't use 4.18 joules per gram per Celsius degree. I was suspecting you could sort that out. Okay, guys, we're going to solve this. You've probably had this experience. Every elementary school in Orem and the surrounding area has a park attached to it. It's actually city law. So, if you've ever gone to an elementary school, you've probably noticed that there's a park, and on the park there's a playground, and on the playground there's a basketball hoop, and above that basketball hoop playground area, there's one of those big old lights hanging off of a pole, and it hums like crazy. And if you've ever looked at that light, you've probably noticed that that light has this weird yellow cast to it. Because those are actually what are called sodium vapor lights. The way that that works is they actually take a filament and they pass a current through it, and that current excites sodium atoms that are in that bulb. Those excited sodium atoms then turn around and re-radiate that energy in the form of light, which has that interesting yellow cast to it. Well, guys, the question that we're going to answer is this. If that yellow light that's given off by this vapor lamp, again used for public lighting, has a wavelength of 589 nanometers, what is the frequency of that radiation? You've got 35 seconds. Figure it out. Most of you are going to get it wrong. It's not comforting, it's just true. Some of you just figured out why you're going to get it wrong. Got it now? You guys get it? Okay, here we go. So we've got C is equal to lambda nu. Guys, what are we solving for? C, lambda, or nu? We're solving for nu, so we need to know the others. And so, guys, C is 2.998? Okay, 2.998 times 10 to the 8th, and that is meters per second. If you did not put units on your number, you probably just rode this blissfully into the ground. Because then, guys, we've got our wavelength, and it is 589 nanometers. And guys, I'm going to stop there. I'm not even going to put the equals nu or times nu, because we've got to deal with this. We have two lengths, but they're not the same units, and therefore they can't divide. So what are we going to do? Well, we got to convert one or the other. This would be my recommendation. Do not convert the speed of light to nanometers per second. Instead, we are going to convert nanometers to meters. Now, guys, you may or may not remember that the prefix nano means what? 10 to the 9th. But now, guys, the deal is this. We know that there's a 9, but it will be a positive or a negative 9. Negative, because we're talking about nanometers, which is a very small fraction of a meter. So, guys, here's what we're going to do. We're going to go like this. We're going to go 589 times 10 to the negative 9th meters. Now, guys, here's the thing. Some of you, this makes you twitchy, because you're going, wait a second, that's not in proper scientific notation. The decimal place should be here. Guys, please don't do that. Because if you move the decimal place over 2 places, you've got to change the 9. But do you change it to negative 7 or negative 11? It doesn't matter. Don't do it. And then you won't make that mistake. So guys, rather than trying to put this in proper scientific notation, leave it like this. And that then is times nu. Now we can solve that for nu. And nu is equal to, help me out, 0. 10 to the who? What are my units? Hertz. Or you can put inverse seconds. So guys, here's what we now know. That when that sodium vapor light is emitting this light, the wavelength of this light, which is 589 nanometers, associates with 5 times 10 to the 14th of these waves being emitted in a second. That's how that wave turns over. It turns over 5 times 10 to the 14th times per second. Yeah. No. Our ears can only hear between 20 hertz and 20,000 hertz. And that's air. That's air wiggling. This is electromagnetic radiation wiggling. The reason that thing hums is because there's something inside the electronics that is wiggling somewhere between 20 and 20,000 times a second. Yeah, no. Okay, all right. So, guys, have this interesting experience then with me. You ready? Remember those two numbers, and then let's go here. So, guys, tell me tell me the wavelength of this light. What was it? 589 nanometers, which puts us, here's 550, here's 575, puts us somewhere in there. But then, guys, if we bring this up to frequency, it puts us somewhere in the middle of frequency. Here is 10 to the 14th. This is 10 to the 15th. So it puts us kind of in between 10 to the 14th and 10 to the 15th. Do our numbers represent that? What was our frequency? 5 times 10 to the 14th, which puts us right in there, halfway between 10 to the 14th and 10 to the 15th hertz. You get the idea? Okay. So guys, we're now comfortable with the interplay between frequency and wavelength, yes? You're good? All right. So guys, this is about to get crazy. Okay. We are now going to talk about something, guys, called quantized radiation. You want to write this down. No. Okay. So guys, the best way to understand and this is not quantized, this is called quantized radiation. The best way for you to understand this is to understand it in the historical context. So guys, what we have now, where we are right now conceptually, is that we understand that light behaves as a wave. And that wave can be described as a wavelength, and that wave can be described as having a frequency. And guys, from looking at that last chart, I hope now you're understanding that the only difference between different colors of light is the wavelength and the frequency. Is that okay? Okay. So now here's what happened. Who was doing that work? That interplay of wavelength and frequency, but applying it to atomic structures. Bohr, right? So here's what Bohr's doing. Just like we did in lab, and again, forgive me if you weren't in lab, but let me invite you into the idea. So Bohr was doing this. Bohr was taking these elements, and Bohr was passing currents through these elements. And as Bohr was passing currents through these elements, he realized that this red light was actually not just red light. He passed it through a spectrum, and he was able to break this out into the different lines. And he began to make this connecting idea between the idea that these different lines, these different wavelengths and frequencies of light, were in some way related to what was going on with the electrons. But here was the thing that he found that was interesting and somewhat troubling. When he was taking this energy and breaking it out into the spectra. Just as you saw when you took that light and passed it through the spectroscope. Guys, didn't we see lines and then dark spaces in between? Yeah? And that concerned Bohr. And it's actually what led him to the planetary model of the atom. So understand that we have history on our side, right? We can look back and we can explain it. And that's how we're going to handle this. But imagine being Bohr and seeing these lines and then these dark spaces in between. Because, guys, his interpretation of that was brilliant. Be careful, Mark. His interpretation of that was brilliant, and let's talk about it. And again, the only way we can do this is by talking about what we know that Bohr didn't know. So we're just going to have this conversation. So guys, what do those lines represent? They represent, who said, Matt? Was that you? Yes. Guys, and that was Bohr's breakthrough. That those lines represent differences in energy. If you have an electron that's here and it falls to here, it releases energy. And so those lines, we're going to find out later, are representative of differences in energy, which he then figured out was falling from high to low. Does that make sense? But what does it mean? I'm going to lead for a minute. What does it mean that there are black spaces between the lines? Consider this. I need a chair. Okay, so guys, this analogy is not very robust. Understand that electrons do not release energy because they hit something. With that said, here's the analogy. Imagine that I'm an electron, and imagine that these places represent energy levels or orbits, okay? So here's the idea. So we're going to say there's 3 orbits. 1, 2, and 3. Good? Okay, so now here's the idea. And I'm going to be an electron. So we take me as an electron and we excite me by passing current through me. But I don't want to stay here. High energy positions are not favored, like balls rolling downhill at spontaneous thank you Gibbs. So, guys, I'm up here in an excited state, but I don't want to stay there. And when I have the opportunity, I'm going to fall back down, and I'm going to release that energy in the form of what? Me, sound, right? But if you're an electron, it comes out as light. But guys, the thought here then is this. If you excite me and then let me fall, and I'm not going to have you close your eyes. Do you want to close your eyes? Okay, so do this. Close your eyes. So guys, remember we've got 1, 2, and 3, right? So here comes 1. I'm falling from 2 to 1. Got it? Here comes 3 to 1. Listen close. Got it? Okay. Now with your eyes closed, tell me which fall I'm about to go through. Is it 3 to 1 or 2 to 1? Which one was it? 3 to 1. How did you know? More energy. I heard you get on the table. Yeah, but you understand the analogy. So now, guys, tell me this. Why is it that I can only release this much energy or this much energy? Why do I only have 2 amounts of energy I can release? Because there's only 2 places I can be. See, guys, I can't stand here. What if I could? Then I could release energy associated with this, right? But I can't because I can't stand there. So I can either do this or I can do that, but I can't jump from here and release that quantity of energy because I can't be there. Neither can electrons.
And that's why there was black spaces. Do you get it? Guys, and this was the thing that blew Bohr's mind. He demonstrated that not only was light caused by falling electrons, but because there were bands of light that were emitted, and dark spaces in between. This is brilliant, right? He supposed that the only explanation for that was that there were places where electrons could be, and there were places where electrons couldn't be. And if that was true, Thomson was wrong, right? Thomson was the plum pudding model. Thomson thought the electrons were anywhere within the atom. And Bohr very insightfully said that can't be. That the light that we see coming out of these atoms does not have every possible amount of energy. If the electrons could be everywhere, they could fall from anywhere to anywhere, and every time you excited an atom, you just get white light. But he realized that there are some falls that are allowed, and there are some falls that aren't happening. They're not allowed. And the only thing that could explain that is there are places where electrons can be, and places where they can't be. And if that's true, then these electrons have got to be organized. And he used the only organizational structure that made any sense to him, the solar system, and that's how he created the planetary model. Does that make sense? Okay. Now, guys, understand Bohr did not do this in isolation. And this is where you need to pick this up. Because a guy named Max Planck or Planck, depending on how you pronounce it, said something interesting. He said this. He said that energy can only be released or absorbed by atoms in chunks of some minimal size. And understand that minimal size is not uniform, but it isn't infinite. That atoms cannot release all amounts of energy in the same way that they can't release all colors of light. And understand that Planck made this statement, proposed this idea as he was working with Bohr. And so he and Bohr are studying the light that's released by atoms. They're breaking this stuff out into spectra. They're realizing that there are dark spaces and lines. And Planck was the first to interpret that and say that the energy that's released by these atoms is not universal. It always comes back to some minimum amount, and that minimum amount is not the same for every atom, but it doesn't change for that atom. And so he coined this term called a quantum of energy. This is where we later got quantum physics. So guys, what is a quantum of energy? A quantum of energy, which is a fixed amount of energy for every atom, is the smallest amount of energy that can be emitted or absorbed as electromagnetic radiation at any given wavelength or frequency. Now guys, I know that this is confusing. Just ride this out. We'll make this make sense in a second. And we're going to make this make sense by going back to our sodium light. Are y'all caught up? Not quite yet? Okay. You okay? So guys, as a result of this, and here's where we need to make sort of the change. As a result of this, remember, because it's Bohr and Planck and they're studying energy as waves, right? Light as waves.
This was where Planck began to suspect that light could also be treated as a particle. And he was then the one taking this idea that coined the term photon. Did it come up? There we go, photons. So guys, think about it this way. We're going to now reconceptualize a light bulb. I mean, it doesn't have to be the lights in here. We could even picture the sodium light in the playground. So guys, up until now, we have pictured a light as a source of radiation that is traveling as a wave, right? But in order to understand what Planck is saying, it's helpful to conceptualize this now instead of a wave, but as a particle. And here's the idea. Now think of a light bulb as, rather than a source of waves, a source of particles. And guys, if you can imagine particles of light coming out of these light bulbs, guys, it turns out that each one of these particles of light, these photons, are actually little packets of energy. And these packets of energy, when they hit us, they deliver that energy to us, and we experience as warmth and sunlight and things like that. But guys, what Planck was doing was he was understanding that this energy that's coming out of the light, while it is experienced as a wave, it can also be described as a packet of energy or a photon. And it turns out that if we are underneath a light and if we are absorbing light from that, or energy from that light, the amount of energy that we're absorbing has to be a multiple of a smaller number. So guys, think about it this way, and these numbers I'm making up, but imagine that the photons of light, of light that come out of this light bulb, each of them have 10 joules per photon, okay? So if one photon hits me, how many joules did I just absorb? 10, 2, 20, 3, 30, 4, 40, and so on, right? So guys, what about this? If this light releases 10 joule photons, can that light give me 23 joules of energy? Why not? Because it only comes in packets of 10, right? And that's what Planck observed, that when light was radiating energy, that energy always came out as a multiple of a smaller amount. And he said that must be because light is a packet, it's a particle, and each of those particles has a fundamental energy. And guys, that's actually what Bohr ran with, because Bohr said, connecting with Matt's idea, if these photons can only have specific amounts of energy, that means there's only a place that they could have fallen from and only some places they could have fallen to, and consequently those electrons can't be anywhere. They've got to be in fixed positions, and when they fall, there's only allowable amounts of energy they can radiate. Does that make sense? And they worked that all backwards. So let's summarize that, because that's important. So here's what Planck determined. He said that lights can only emit energy in multiples of a smaller number. That smaller number must be the amount of energy in a particle of light that he called a photon. Then Bohr grabbed a hold of that and said, if that's true, then that means there's only some places electrons can be and all the other places they can't be, because if they could be in all possible places, we would have photons with all possible energies. And because we're not experiencing that, that must mean that the electrons are organized. Do you get the connection? Okay, so guys, what they did then in collaboration is they put together a way to describe this. And this was the brilliance, is they then connected the particle-like photon with the wave-like frequency of light. Because it turns out that the energy of one of these photons is actually related to its frequency. Yeah. It's super high energy because it's super high frequency. Exactly, Tyler. That's exactly right. Okay, so guys, this then is the relationship. Simple, right? E energy is equal to H nu. Now, guys, H is actually what we call Planck's constant. And its value is 6.63 times 10 to the negative 34th joule seconds. And then nu we already know to be frequency. And then, guys, bringing this full circle, and then we're going to do the math. This was then Planck's idea that matter can only absorb and radiate energy in multiples of h nu. Why? Because that energy is coming from falling electrons, and there are some places electrons can be, and some places those electrons can't be. Let me answer in a minute. I want to do the math first, and then we'll do questions. Isn't that fascinating, though? It's really cool. Thank goodness for smart people. You guys caught up? Okay. So, guys, let's go back now and do this. Says calculate the smallest increment of energy, that is the quantum of energy, that an object can absorb from a yellow light whose wavelength is 589 nanometers. Sound familiar? That's our sodium light, right? So guys, what we're asking now is this. When this sodium light radiates energy at 589 nanometers, how much energy does each one of those photons possess? Well, guys, notice that we've got two equations. We've got C is equal to lambda nu, and then we've got E is equal to h nu. Now, guys, we want to solve for E, right? So what do we need to know? We need to know nu. We need to know the frequency. But nu is right here, but we already solved this. So we've already done half the math. So now we can just look at this equation. So E is equal to Planck's constant times the frequency. So what is the energy of one of these photons of yellow light? Well, guys, we need Planck's constant. 6.626 times 10 to the negative 34th joule seconds times, what was the frequency? 5.09. 10 to the 14th, inverse seconds. Notice that the seconds cancel and we're left with joules. I'm counting on you to have the calculator. What'd you get? 3.37 times 10 to the negative 19th joules. So guys, what does that mean? Well, it means when you're playing basketball on that playground, the energy that is coming out of that yellow sodium vapor light as it is transferring energy to you is transferring energy in multiples of this number of joules. So if one photon hits you, that many joules. 2, double it. 3, triple it, and so on. But all that sodium vapor light can do is radiate energy in multiples of that amount. Do you get the idea? Okay. So guys, bringing this then full circle, because I know that a good number of you are actually musical, I think you're going to like this. Guys, this then is what Bohr and Planck said. They said that nature is more like a violin than it is like a piano. See, the difference here being that on a piano, you can drag your fingers up the scale and you can play all possible notes. But on a violin, there are some notes that are allowed and some others that aren't. And I know the analogy breaks down because you know more about music than I did, but they were trying to relate this to things that they could express in the world that most people were familiar with. And so the idea is that they said that matter has places where it can exist and places that it can't. More like a violin than it is like a piano where you can just drag your fingers up the scale and all potential positions are possible. Or if you don't like that, I actually prefer this one. Nature is more like a ladder than it is like a ramp. That one makes more sense to my brain because I have no musical skills whatsoever. On a ramp, you can stand at any elevation. On a ladder, there are some places you can and some places you cannot be. That makes more sense to me. But guys, this was the beauty of Planck and Bohr's ideas, which led us to this organized idea of the atom as we think about what will eventually become energy levels and sublevels and orbitals. So there you have it. You've been waiting. Go ahead, Brandon. Mm-hmm. Exactly. They work. Yes. Yeah.
Statistically, and it always proved to be.
It always came back to the same magic, right? They knew the energy. They were able to measure the energies that light was transmitting. They were able to measure the frequency of that light, and then by dividing, they always got the same number. That's cool. Imagine making that discovery. You knew you were onto something if you had that happen. Yeah, imagine that. Pretty cool. So, guys, y'all set? Okay, so here's your homework. Goes like this. I'm going to